All right, so is less than. It's going to take in two strings, and we want to return true if the first string A should come before the second string B. How do we handle upper and lowercase letters? So for instance, which should come first? Cat or cat? So this is actually an interesting thing. So when we think about, generally speaking, we would probably say those are the same, right? So I'm going to show you here in a few minutes, there's a function built into Java that'll do the comparison we're doing, but the type of comparison it does is called lexicographic comparison. So a lexicographic comparison is alphabetic, but what it does is it takes into consideration the Unicode values. All right, so which Unicode value is smaller, the lowercase c or the capital C? I think the lowercase c is 60 something, the capital C is 90 something. Yeah, so we would say that lowercase cat comes before uppercase cat because, I'm pretty sure I don't have that mixed up. Yeah, and the upper came after the lowercase ones, yeah. So in that case, if we lexicographically compared these guys, lowercase cat would come before uppercase cat because lowercase c actually does come before uppercase c. That makes sense? Now, if we wanted to be purely alphabetic, what we could do is we can make both strings lowercase. Does that make sense? All right, so we could also do that. So just out of curiosity then, pause this guy for a second, just in case we need something like that. I'm just going to just make this guy a void for a second so it doesn't give me an error. So what if I have a function static string to lowercase that takes a string as a parameter, and I should return the lowercase version of that string? What things do I need to turn into lowercase? From A, anything that's an uppercase letter, right? So first I need to identify things that should become lowercase, correct? So I'm going to need my string uppers is going to be A, B, C, D, F, G, H, I, J, K, L, M, N, O, P. All right. And then I'm going to also need string lowers. Yay. All right, so those are all my lowercase letters. So I'm going to build a new string, okay, from my original string. So when I build a new string, I like a nice clean foundation, right? So I use the empty string as my source. So we'll say string answer is equal to the empty string. Then I'm going to go through every single character in A. How many letters are in A? How many characters are in A? A dot length number of characters. So I is equal to 0. I is less than A dot length. I plus plus. So as I go through here, I want to find out if the current character I'm looking at is found in here. Then I need to do something special. If it's not found in here, I just want to keep it, right? That means it's not an uppercase letter that needs to become lowercase. So how do I ask the question? How do I get the current character I'm interested in? So A dot char at I. Okay, so A dot char at I will give me the current character I'm interested in. And I want to ask the question, is that character an uppercase letter? How do I ask that question? Okay, and how do I ask? Is it part of string uppers? Pretty similar to our remove vowels, or what was it, print vowels and print consonants and print digits, those guys. So you mentioned we use index of. So I can say if uppers dot index of that character, if it gives me something equal to a -1, that means it was not found in there. If it was not found in there, what do I want to do with it? That means it's not an uppercase letter. Therefore, I don't need to change it. So I want to just add it to my ongoing string, the string I'm building. Leave it alone, add it as is. So this will be answer is equal to answer concatenated with a.char@I. Just keep it. No conversion necessary. Else, we need to convert from upper to lowercase. How do we do that? If I'm in this else, I know that I found the value inside of upper. How do I convert that value to lowercase? So lowers dot char@I. Okay. Yep, so just like that. Nope. Close. It's not horribly wrong, but this guy right there is pretty suspect. Because what's I? I is our voyage through A, which might be significantly shorter or significantly longer than this guy. If I'm looking at an uppercase A, that should become a lowercase a, right? What position will I find an uppercase A at inside of uppers? 0. And what position is lowercase a in lowers? 0. So I need to get that index of this guy again. So I want lowers dot char@ whatever the index of that uppercase letter was. Now, you might not want to call index of twice here, so we might do something like int pause is equal to that. Then we can ask the question, if pause is equal to -1, do that stuff. Otherwise, go ahead and grab the character at bucket pause inside of lowers. So if I found A at pause 0, give me lower at pause 0 to give me the lowercase version of that. Okay, if I found pause is whatever bucket that is for M, so let's go 13, 12, something like that. Then I'll get the same bucket over here on this guy. All right, because these two strings are parallel strings. They match each other for the alphabet, just one has the uppercase letters, one has the lowercase letters. Okay, so as I go through my string A, whatever string was passed in here, if the character I'm currently looking at is an uppercase character, well, if it's not an uppercase character, that's what that says, then just go ahead and tack it onto my answer. Must be either lowercase or a space or a question mark, something that was not found in here. Otherwise, if it was found in here, grab the equivalent position value from here and tack it onto my answer. When all is said and done, go ahead and return answer.
So lowers at pause means the chart, the position in the uppercase one from looking to the left.
Yep. So if this is 0, 1, 2, 3. So let's say we happen to be looking at capital D. So that means index of capital D is going to give me a 3. Char at 3 here will give me a lowercase d. That gives me the character at position 3, which happens to be a lowercase d. So index of and char at are kind of inverses of each other. Index of says, where in this string is this dude located? Char at says, get me the dude located at this index. All right. So let's test 2 lowercase here. We'll just write it here at the end. Oh, actually, this will be fun. Let's just go into our print array down here at the bottom. Oh, I'm going to have an error in here for right now, so we won't test it right now. Just trust me, it works. All right.
Sorry, could you explain again your difference between index of and char?
So index of returns the position in a string where a character lives. Char at returns the character at a position in a string. So index of capital A gives me a 0. Char at 0 gives me a lowercase a. Make sense? All right, so if I wanted to convert stuff to lowercase and do a direct comparison that way, we could. It would no longer be a lexicographic comparison, then it would be an alphabetic comparison. All right, so we can choose if we want to do that or not with this is less than. It's not going to change the length of our 2 values, correct? So I can certainly say A is equal to driver dot 2 lowercase a. B is equal to driver dot 2 lowercase b. And that'll convert those guys to lowercase. There also happens to be, I could have also said A is equal to A dot 2 lowercase. Strings know how to convert themselves to lowercase. But if I would have told you that first, we wouldn't have had the joy of writing the method. There's already a built-in one. Okay, so we'll use ours, because ours is probably better anyways. So we'll convert our A and B to lowercase versions of themselves.
So lowercase is the syntax itself?
So this is the one we wrote.
I know, right.
But this string class has built into it, just like they have a char at method and an index of method, they also have a 2 lowercase method and a 2 uppercase method. So they can convert themselves to lowercase or uppercase as well. But that's no fun. Might as well write our own, right? All right, so now that we know we're dealing with lowercase strings, we'll go ahead and do an alphabetic comparison. Okay, so we know that A and B are lowercase. We know that chars to check is going to be the smaller length of the 2 values. Okay, so we know with confidence that we'll never access an index that's illegal inside that for loop. Okay, we're dealing with the same. You know, we're dealing with whichever is the shorter number, or the shorter length string. So each time through here, we want to ask, is the current character we're looking at in A, should it come before the current character we're looking at in B? So if A dot char, where did that come from? A dot char at I is less than B dot char at I. And we're allowed to use less than in this case because this is a char, which is a numeric type. It's a Unicode value. So is the numeric version of this character less than the numeric version of this character? Okay. If it is, that means that the first string comes before the second string. Because we're comparing character by character by character, and as soon as we hit one of those, where the first string's character comes before the second one, we can return true. Because if A comes before B, return true. Switch this guy back to a Boolean return type. So if the current character we're looking at in A should come before the current character we're looking at in B, return true. Otherwise, we're going to keep trucking. Okay, otherwise, we're going to keep trucking. Now, if I'm still alive here, that means up to this point, the strings are the same. That make sense? Which means that we decide the shorter one comes first. A true statement. So return false. So this is going to give us every opportunity to prove that that string A comes before string B, comparing character by character by character by character. But as soon as we finish that, if we haven't been able to distinguish them for the first, whatever the chars to check number of characters, then the shorter one comes first. Make sense? Huh? Well, you don't need an else to this, because what would we do in the else? We could put an else, but this says if the first character should come before, if the character we're currently looking at in A should come before the character that we're looking at in B, that's actionable. That means that we actually need to do something. We're done. We finished finding the answer. So we'll go ahead and return true. Yes, I can declare that A is the string that comes before B. If it's not less than, if it's either equal to or greater than, there's nothing we would do. Alternatively, we're just going to move on to the next character. Does that make sense? Now, having said that, we could actually increase the efficiency with an else. We could say else if a dot char at I is greater than b dot char at I. If that's a true statement, we could actually return false right there. That make sense? Because that means that B is actually the smaller string, the string that should come first. So why go through and check other stuff when we could just detect it right here? All right? So we'll return false there. If we get to this point, we know that they're the same. Up to this point. They're identical strings up to the number of characters chars to check. And then we'll return false because the smaller string is the should be the winner. How do we know which is the smaller string? This makes the assumption that A was the smaller string. So really, we should only return false if B was the smaller string. So here, we need to figure out who's actually the smaller string. So if A dot length is equal to chars to check, that means A was the shorter string. So we'll return true. Else, return false. So what we're really doing here is we're saying the strings are the same up to this point, so return based on the shorter string. So we had to ask the question, who was shorter? If A's length was equal to the minimum value of the two lengths, then return true. A was the smaller string, therefore A must come before B. Otherwise, B must come before A, because B was the shorter string. And that's only if we're still kicking after this for loop and we didn't return inside here. Because the return statement makes a method immediately end. Right? So if we get inside of this if or this else if and we return, we will never get down here. That method immediately ends and returns its value. All right, so now we have an is less than function that we can pass two strings to, and it will return true if the first string should come before the second string. So I can now go down to my merge sort, and I want to know if this string should come before this string. So I'll say driver dot is less than, and A will be this guy, B will be that guy. If that's the case, first string wins. Otherwise, second string wins. Then copy them back. So now let's come up here. Here's the proof of our original array. And we'll say driver dot merge sort, passing it AR, passing it 0, and passing it AR dot length -1, the last legal bucket. Then we'll print out our sorted array, which should be sorted alphabetically now as opposed to lexigraphically. So, looks alphabetic. The Y's and Z's come last, the A's and B's come early. We'll just assume everything in the middle looks legit. Okay? So, questions about that? Now, we did some extra stuff there, right? So one thing you noticed here is that there was a couple of characters where we had, let's see if we have any obvious examples here. Yeah, here, like uppercase F, lowercase f, these guys. So this guy came before this guy because it was not because it was a shorter string, but because the G came before the S. We treated the two F's as equals. That make sense? Because we lowercased this guy when we did the comparison. That's an alphabetic comparison. A lexicographic comparison would say this guy's Unicode value is actually greater than this guy's Unicode value. Therefore, these two would be flip-flopped. The one with the lowercase f would come first because lowercase f comes before uppercase f lexigraphically in the Unicode character set. Lexigraphically doesn't actually mean Unicode. It means the underlying character set, the numeric value for it.
Okay, so when we were creating that method, we were replacing uppercase, lowercase, we're just...
Correct. I made sure both strings were lowercase.
Okay.
So there were 0 uppercase letters in any of my strings when I was comparing them. There's still the original string later on, because when I pass them in, let's go down to our yeah, here's the is less than. So when I pass in my two strings to is less than from merge sort, I'm passing in strings with upper and lowercase characters in them. The very first thing I do is I convert those two guys locally only to their lowercase equivalents. So after these two lines of code, A and B are all lowercase. Okay, it did not impact the originals. Okay, but as far as my comparison goes, I've ignored uppercase letters. Everything's now lowercase, so we're on an even playing field, if you will. Now, having said that, we still are doing a lexicographic comparison when it comes to things like question marks and spaces and that kind of stuff. We know we don't have those in our code because we generated our strings out of letters, upper and lowercase letters. So we can say with confidence that we're actually doing an alphabetic comparison right now because we know we only have letters and we're being case insensitive because we made everything lowercase before we compared. Okay, so we're doing truly an alphabetic comparison, which is fine. I mean, one's not better or worse than the other. It's more just know how your comparisons are working, right? Just so if you wanted uppercase letters to come before lowercase letters, you're going to do it differently. Right? So in this case, we're treating upper and lowercase as an equal playing field. That's not the deciding factor. We're converting it to lowercase and doing the comparison. Okay, so now let me show you the version of this guy that wouldn't have required us to write two lowercase or is less than, any of that stuff. All right. So strings, and let's actually go to our keynote. Let's throw down a couple of new functions that we've been introduced to here. So we did a little shopping spree to Home Depot, right? More string functions. So I showed you 2 uppercase, 2 lowercase. So that converts the calling string to uppercase, converts the calling string to lowercase. But converts is actually the wrong word. This returns a copy of the calling string in all uppercase. This guy returns a copy of the calling string in all lowercase. That is to say something like string s is equal to hello. String s2 is equal to s dot 2 uppercase. S2 would be hello in all caps, but S has not changed.
And is it in a different location?
It would be in a different location because it's a whole different string. So what this guy does, when I call 2 uppercase on, in this case, S is the calling string, I'm saying convert this guy to uppercase and return that copy, but don't change S. So after that line of code, S is still hello in all lowercase. S2 is the uppercase version of that. Okay, so it's non-destructive. It's working with copies. And 2 lowercase works the same way. That make sense? All right, so now the other string function, what was I talking about? Oh, we're doing the, so we have a string function called compare to. And this guy takes in, go ahead.
Are these functions any different from the ones we just created?
These are ones that are built into strings. They come with strings. So these are sitting there right next to char at and index of. So these are tools that we actually already had available to us, but I didn't tell you about until now.
Right. But is it the one we just built? Does he also return a copy, or
For 2 lowercase?
Yeah.
Yeah, he does.
okay.
Just to show that, to connect the dots. If we go to 2 lowercase, wherever I wrote that, 2 lowercase, I build onto a new string. So there's my answer. I build up that answer and ultimately return that dude. I didn't change A at all. I made no, in fact, strings are read-only anyways, so you couldn't change a string. And we'll talk more about that now. Let's just throw that behind. If you wanted to change the, well, we've kind of seen that before, where, you know, if we wanted to remove a single, you know, bucket 3 from a string, for example, I can't just say get rid of bucket 3. I have to build a brand new string and just keep everything except bucket 3. Strings don't. That char at method is a one-way street. I can get the value at bucket 3, but I can't change the value at bucket 3 in the string. Okay, it's one way. Whereas arrays are read-write. I can access bucket 3, but I can get the value at bucket 3. I can also change the value at bucket 3 directly. Does that make sense? Okay, so arrays have the flexibility of being read-write. They also have the flexibility of having, they can hold more types, where strings are collections of chars. So on one hand, you might say, oh, well, that means arrays are good. Well, strings have a whole lot of crap built into them. You know, it seems like every few minutes I'm introducing more things that strings can do out of the box. I just happen to introduce them a little bit late, you know, after I've seen the misery. Wait, isn't this fun, writing all these functions? I mean, these are easy ones compared to what you'll have to do for your homework. So we have another function built into string called compare to that takes another string as a parameter. And this guy returns a value less than, and actually, hold on, let me put the return types for these. that guy returns a string. This guy returns a string. This guy returns an int. So compare to takes another string as a parameter, returns a value less than 0 if the calling string comes before another string. That is the string parameter. Returns a 0 if they are the same, and a value greater than 0 if the calling string comes after another string. Okay, so compare to returns a numeric value. Something smaller than 0, it's usually a -1, but the guarantee, so compare to is actually a kind of a dinosaur. I'm teaching you the Java version of this, but this is something that came from a much older language. Java's implementation, I haven't actually looked at it in a very long time, but I am pretty certain it returns -1, 0, or 1. But the official way to teach it is it gives you something less than 0 if the calling string came before the string you passed in, lexigraphically. It returns a value greater than 0 if the calling string should come after the string you passed in, and it returns a 0 if they're equal to each other. Does that make sense? So to use this guy in place of our is less than function that we wrote, we want to ask the same question that we asked down here, just using compare to. So instead of saying, and here what I'll do is I'll comment that out, and we'll rewrite that else using the compare to, just so you can see them next to each other. So else if AR at bucket begin 1, which is a string, that guy will boil down to a string, dot compare to, actually, if we want to, well, let me show you this one first, and I'll just tell you about the other one. And I'm comparing him to this guy. And I want to know if this first guy is less than the second guy. So that means if this returns a value less than 0. Well,
in terms of writing
well, no, because index of the -1 thing, I mean, it does, they both return integers, but the -1 is the evidence of not finding it there. Where this, it returns either something smaller than 0, a 0, or something greater than 0. So there's really kind of 3 stages, 3 different things that can happen. It can say, this string comes before this string comes after this string, or these 2 strings are the same. Those are the 3 different pieces of information we can get from compare to, depending on whether the value that was returned is less than 0, equal to 0, or greater than 0. But because the question we're asking here is, which wins? The string there or the string here? The string here wins if he should come before this string, alphabetically. All right? So that's how we would write that. Now, as it is right now, let's see if we happen to luck out with our example. This guy does it lexigraphically. All right? So that means that it will put lowercase a's ahead of uppercase a's, because of where they occur in the Unicode character set. There is a compare to ignore case version that I'm sure converts both strings to lowercase before it does the thing. So if it really is important that you are doing an alphabetic comparison versus a lexicographic comparison for whatever problem you're solving, if that is a deal breaker, there is a function here, compare to ignore case, that does exactly that. But again, that still assumes that it's still doing lexicographic if you give it stuff like question marks and things like that. But if you're only giving it letters, then it'll do alphabetic like we wrote. All right, so this should be the same thing, except it's lexicographic. Let's just see if we happen to have a tie anywhere in here. Oh, yeah. There's a big one. So it actually must have been reverse, what we said. The uppercase must come first. So notice that all the lowercase letters came later on. See this? And we could prove that real quick. Let's just come up here real quick and we'll just do a system.out.println int version of A int version of A. So this guy must be 90 something, this guy must be 60 something. Those would be the first two things we see up here. Yep, 90 something, 60 something. So understand the difference between lexicographic and, okay, so that's probably not really what we're looking for here, right? So we probably want the other version of that guy, the compare to ignore case, because we just had a pretty good eye-opening experience with lexicographic is going to kind of cut our data set in half. They're sorted in and of themselves, but they're so it's compared to ignore case, I think is what it is. And now we get it alphabetically. That makes some sense? All right, so technically I'll throw compare to, let's say also a compare to ignore case version. Something like that. Okay, so that's merge sort working on a couple of different types. All right, so let me go ahead and why don't I give you this code. This thing really scrolls very slowly. Yeah, well, possibly, but I actually think it has to do with the giant touchpad that's on the new MacBook Pros. I mean, this touchpad's like the size of my hand. It's ridiculous. So let's throw this in here as new string functions plus string merge sort. Something along those lines. Just some more reference stuff before I delete a bunch of stuff. All right, so we're good with that. Oh, God. Well, there's 2 hours of work down the drain. All right, so let's introduce the next stuff. So the next thing we want to look at here is, let's see, I want to do, sort of kind of already did that. Let's do two-dimensional arrays. So 2D arrays. So up to this point, we've looked at single-dimensional arrays. Okay, really 2D arrays should be multi-dimensional arrays is the multi-dimensional arrays would probably be the appropriate thing because typically we would have 2 and 3-dimensional arrays. So a one-dimensional array like we've seen here creates a whole bunch of memory in a row, so contiguous memory for holding like types. All right, now a multi-dimensional array is a collection of collections. It's effectively what it is. Or an array of arrays, at least in a two-dimensional array. So let me show you this as an example. Whoa, what did I just do? I hit the title magic button there. Does that go back to normal? Nope. Well, that ship has sailed. Back there. Body. See, they think this magic bar is so slick. You just constantly end up hitting stuff. Only good use I found for it so far is tennis balls. And I found a couple other emojis. Oh, let me see. Did I show you the lizard one? I did or didn't? Because I found a lizard emoji. It was really cool. Very exciting. What was I talking about? Oh, tennis balls and the arrows on the ends of lines. It's the two things it's good for. Everything else, it's nothing. Waste. All right, so collection of collections. Now I'm going to let's create a multi-dimensional integer array. So I'm going to create an integer array, a two-dimensional integer array. All right, and this guy, we'll call him AR. He's going to be a new integer array of size. Usually I think about this as rows by columns. Okay, doesn't actually matter how you want to think about it, as long as you always think about it the same way. I usually think of the first number as being rows, the second number being columns. Okay, if you're thinking about this guy as a grid. Okay, a three-dimensional array would be like a cube, right? And then four-dimensional arrays, our mind goes into an infinite loop. They exist. You can make a four-dimensional array, but we don't have good applications for those because we can think in 2 dimensions, we can think in 3 dimensions, and then things stop making sense, right? So typically you will see 2-dimensional arrays are somewhat commonplace for certain problems. 3-dimensional arrays every now and then. Anything beyond that it would be pretty rare, or just I've seen some 4-dimensional arrays, I think, for some encryption algorithms, and I think part of it's just to be confusing. Like it's part of making it difficult to understand so that it's more secure. It's like it's security through obscurity. So in any case, this will create for me a 2-dimensional array with 3 rows and 5 columns. Just like a normal array, this is an empty husk. There's nothing in there yet. All right, it's just a bunch of empty buckets. But the interesting thing is, what do those buckets look like? Like what does the structure look like? So I'm gonna steal this guy. And then let me steal this line right here so we can use that as our reference. All right, so that's what we are creating. So here is our, so actually I got to draw this downwards, right? Since I said rows by columns. I kind of don't want to, well, I'm going to draw it sideways, that way I can keep this stuff intact. So these are my rows. You can think of that kind of, we have to turn it on its side to be the individual rows, but whatever, to create our grid. So there's going to be 3 rows and 5 columns. What value lives in each of these? Is the first question. So if I come out here and I say int array AR is equal to a new int array 3 by 5, what's the output of this program going to be? Memory addresses? Okay. Those are your 3 memory addresses. So we just printed out this value, and this value. A 2-dimensional integer array is an array of arrays. Yeah, this is 2-dimensional. This is first dimension, this is the second dimension. This is 3 by 5, 2-dimensional. So this guy is an array which points to 3 other arrays. I'm going to take off the memory addresses here just to keep this a little bit smaller. So each bucket of this array, this 3-bucket array, points to a 5-bucket array. Does that make sense? So this first array is an array of memory addresses. It's an array that points to, that has 3 buckets that each point to the beginning, the base address of 3 other arrays. And each of those arrays holds 5 of those guys. Does that make sense? 5 integers. The first array stores the addresses.
Right, but in what, I just can't think of a way to apply it.
Oh, like what would we use this for? Okay, well, don't worry. We would use it for any time that we need to have a grid, because this is going to give us a grid of integers. We will truly have a grid of integers here. It just so happens that the way it has to represent that grid of integers is through an array of integer array pointers. That's the way it happens under the hood. So if we were to draw a picture here of what this guy actually looks like. Take this guy off. From a problem-solving perspective, it's that. Make sense? It just so happens, though, that this is row 0, this is row 1, this is row 2. That these guys are actually pointed to by these guys. So row 0 here is this guy right here. But we get to that. This is row 0. This guy is an integer array. And what got us there is a pointer to that integer array.
So the array with the address is supposed to rows, and then the array is supposed to columns.
Yep. I think that's how it actually is implemented. From a problem-solving perspective, what we're doing here is we're kind of learning how it actually works under the hood. From a practical perspective, we can think about solving problems like this. All right, so for instance, if I want to go ahead and fill this up with random stuff. All right, so we'll do a 3 by 5 grid of, let's do random numbers between 0 and 9. So I'll go ahead and get my So I'm going to go for each row, do that. For each column in that row, I need the second counter there. Do that. And then set AR at IJ. So at row I, column J, equal to R dot next int 10. That'll give me a number between 0 and 9. All right. So this first for loop says for each row in our grid. So I is 0, I is less than our array's length, I plus plus. Then for each column in the current row's length. Does that make sense? So this says go to row I and tell me the length of that guy. Okay, in this case, the length is going to be 5. Okay, the way we built these arrays is to have fixed lengths. Older languages, and Java has a way of doing this, would allow you to omit this last piece there and force you to fill that guy up with actual arrays. Okay, so I'll show that to you. But let's do it with the 5 here first. All right. So this says,
The first line is just defining the size.
this defines the array. So remember our original arrays that we maybe wrote were int array, we'll call this guy AR2 is equal to a new int array of size 20, that kind of thing. So this is how you build a single dimensional array. This is how you build a two-dimensional array. So this is an array. So and actually the syntax is consistent. This says build me an array of these guys. This guy says build me an array of those guys. An array of integer arrays. Does that make sense? So my type here is an array of ints. My type here is an array of integer arrays. So this effectively is going to create a 3x5 grid. This first for loop says for each row, then for each column in that row, let's go ahead and put a number between 0 and 9. Now let's go ahead and give ourselves a function for printing a grid. So we'll say static void, we'll call it print grid. This guy will take in a two-dimensional integer array. And we'll say for int I is equal to 0, I is less than ar.length, I plus plus. For int j is equal to 0, j is less than ar at bucket I.length, j plus plus. System.out.print ar at bucket I, j. Now what I'm going to do, just for pretty formatting stuff, is I'm going to concatenate onto that. This is the escape character for a tab. This will just make it look prettier for when we print the text out. So this will print a number, followed by a tab, followed by a number, followed by a tab, followed by a number, followed by a tab, so on and so forth. Now, after we have finished all of the columns in the current row, we want to go ahead and kick it down a line. So that'll kick it down to the next line. Okay? And if you want to have it spaced a little bit better, almost kind of like a carriage return of lines, you can maybe do a couple of carriage returns. It'll put a couple of spaces between it. So \n is the escape character for a line feed. So that's like pressing return. Okay? So I press return once, then I press return two additional times. So this will be 3 returns. That'll actually happen here before we go on to the next row. So we'll do driver.printGrid. We'll pass it AR. And let's see what our grid of random numbers between 0 and 9 looks like. Looks like that. Pretty good spacing if I do say so myself. If I just do maybe one more carriage return, would it be a square then? I'm just saying that looked pretty legit. That's all I'm really saying. Yeah, see, that doesn't even fit. Yeah, whatever. We'll go back one. Yeah, I'm good with that one. It's pleasing to the eyes. All right.
So for the first one, for the first function, or the first method, you just fill it in the numbers.
Yeah, well, I'm not even using that array. So this is in main, so I constructed the array, went to Home Depot, grabbed my random number generator, then I filled the grid. This says for each row, do something. For each column in that row, do something. Set that row column value equal to a random number between 0 and 9. And then I happen to write a function that knows how to print any grid. And that takes in a two-dimensional array, and it goes through and it prints it out. Okay, so now let me modify this a little bit. So what I'm going to do is I'm going to change that value like that. I think current version of Java will let me do this. Now what I'm going to say is I'm going to say AR at bucket 0 is equal to a new int array of size, let's do 5. AR at bucket 1 is equal to a new int array of size 7. AR at bucket 2 is equal to a new int array of size 9. So because I did not specify the number of buckets that I wanted, the number of columns I wanted in each row, this is creating an array of integer arrays without it automatically generating the size of each of those integer arrays. So then what I did is I manually said bucket 0 is of size 5. Bucket 1 is of size 7. Bucket 2 is of size 9. I don't have to change any of my code down here because I wrote it such that I said how many buckets are in this rows array. AR at bucket I says give me the pointer to the array that bucket I points to. When I is 0, it points to this array. When I is 1, it points to this array. When I is 2, it points to this array. So that length will be 5 the first time, then 7 the next time, then 9 the next time. So there's my 5, there's my 7, there's my 9. That makes sense? Kind of a little bit less useful, because now it's hard to find perfectly legitimate. Doesn't break the logic of a multi-dimensional array at all. But at the end of the day, it's like, you know what? This nice syntax for letting me choose the size of each row probably is there for a reasonable reason. Maybe that reason is that typically if you're using two-dimensional arrays, it's because you're doing something with a grid. You asked earlier, what are practical problems for this? We can come up with several problems that would benefit from a grid. Might be a little more difficult to come up with problems that would benefit from a row with 5 buckets, another row with 7 buckets, and another row with 9 buckets. A little bit. That'd be a little bit more specific, or a very specific type problem. But because of the way arrays work, this is not inconsistent with what I showed you initially. It just so happens that we chose to give ourselves variable length arrays here rather than rely on the default syntax to give us consistent length arrays. Does that make sense? It's still an array of arrays, any way you cut it. All right, so questions about this? And let me say one more thing real quick. Notice that here I said AR.length. That is how many elements are in How many rows are there in AR? That's this dude, the 3. Okay, that syntax is required. This inner loop says, how many buckets are in the array that guy boils down to? So AR at bucket I is an array. Right? When we deal with two-dimensional arrays, these are arrays of arrays. So when I say AR at bucket I, I'm saying go to bucket I, bucket I, bucket I, take me to the array that lives there. Tell me how many buckets are in that guy. What's that guy's length? Does that make sense? So even though this might look a little weird saying AR at bucket I dot length, what lives at bucket I is in fact an integer array. Does that make sense? Therefore, it has a collection of integers and its own length. Okay, so let me put that back to a 5 here. I'll comment out these lines just so you can have them for your records. I'll run this again real quick, show you our 3x5 grid.
So you just, for the first one, you used I and J because they're pointing to 2 different arrays? Or the 2
Well, I just needed 2 separate counters. So typically our go-to counters for like throwaway variables in most programming languages are I, J, and K.
Okay.
You can call them, you could say int rows is equal to 0, int col is equal to 0. You can name them whatever you want. Just typical naming conventions is this variable is a very temporary throwaway variable. And I has kind of traditionally been your first counter variable. If you need a second counter variable inside of the same scope that the first one lives in, you got to pick a new letter, right? So J has kind of, he's the fallback, and then K is the fallback to the fallback. Then after that, it's a free-for-all, is what it comes down to. Okay, so questions about any of that? Let me give you that code. Guess I'd rather you guys use my code than whatever you're finding on Google. Huh? Who wouldn't? Half that Google code was probably my students. Well, not half, maybe a third. I wonder how many programming students I've had, guessing several thousand programming students over 18 years. It adds up. I mean, some of these groups have been, this group's pretty bad, but some of them have been worse. All right, multi-dimensional arrays. Okay, so we'll put that up. And then let's take a 6-minute break. Come back at 8:30 because I need to introduce objects and give you enough stuff for your homework.